Today we're going to talk about complex numbers. All right, I can fight with the construction noise, but I'm not going to fight with you guys too. Y is the imaginary axis. X is the real axis. Let's say we have some imaginary number, some complex number rather. There are two ways to represent a complex number. Anyone? X plus IY, known as rectangular form. Or REI to the, this should be a capital A. Rather polar. Familiar? Sort of? You guys didn't do complex numbers? No. Okay, so I is equal to the square root of -1. Okay, anybody vaguely remember this from high school, hopefully? No. Never done them. Great. Okay. Great. So the example for today is something that half of you have never seen. Excellent. But you don't really need to understand complex numbers to sort of understand what we're going to do today. So complex numbers, for example, if we're taking the square root of -9, well, what's the square root of a negative number? Well, it's not a real number. It's a complex number. So it'd be 3i rather. 3 times I. Okay. So we could have 2 plus the square root of -9, and then we'd have 2 plus 3i. Okay. This is one way for representing roots, the square roots of negative numbers, complex numbers. And there's two ways. One is rectangular, where we've got some x coordinate, which is real, and some y in the imaginary axis. So this would be the 2 plus 3i here. This would be on the x-axis, and that would be the y. The second way of representing a complex number is polar, in which we have a magnitude, or the length of this line, and some angle, A, and we get that number as RE to the IA. Okay.
Is that I times A?
I times A, yeah. Okay. And we don't really need to understand complex numbers all that much. I believe yes in radians. No. Okay, so let's say we have this. We've got some complex numbers and we want to operate on them. Let me just tell you, if we're going to add complex numbers, let's say we're going to add two complex numbers. Would it be easier to add them in this format or in that format? The first one. So if we have x1 plus iy1 plus x2 plus iy2, well, that's going to be equal to x1 plus x2 plus y1 plus y2. Similarly, subtraction is also going to be easier when we're in rectangular format. x1 plus iy1 minus x2 plus iy2 is going to be equal to x1 minus x2 plus y1 minus y2. So that's addition and subtraction of complex numbers if we're using rectangular. Now, if we're going to multiply the numbers, which form is probably going to be easier to use? Polar. So if we've got two polar numbers, r1 times e to the I a1 times r2 e to the I a2, chunk. That's going to be equal to r1 times r2 e to the I. What are we going to do to these? Add them. a1 plus a2. Finally, division. r1 e to the I a1 over r2 e to the I a2 is going to be equal to r1 over r2 e to the I a1 minus a2. So let's write scheme procedures. And let's assume that we've got some constructors and some selectors. Let's assume that for rectangular numbers, we have real part and imag part. And that'll pull out, the real part will pull out the x, imaginary part will pull out the y. And then for polar numbers, we have magnitude and angle. Okay. So those are going to be our selectors. So given a complex number, if it's in polar form, we use magnitude and angle to get the r will be the magnitude, a is the angle. And then if we have a rectangular, we can use real part and imaginary part. Okay, and then we're going to have a couple of constructors, and those are, and those would be, okay, make from real imag. So this is going to put a complex number together. Make from real imag, from a real and an imaginary part, an x and a y. And then we're going to have make from mag angle to build a complex number out of a magnitude and an angle, the r and the a. Okay, so these are our selectors. And these are our constructors. Given those selectors and constructors, let's write a procedure to do this. So I'm going to call this add complex. I'm going to take a number z1, z2. What do I want to do inside this procedure?
First extract the real and imaginary components and then add them.
Okay. So we could just say add. Well, rather, do we want to do that? What do we want to return?
Oh, we need to combine them.
We need to return this as the real part of our new imaginary number, this as the imaginary part of our new complex number, and then paste those together. All right, so we need to use the constructor. Make from real imag. Okay, so how do I get the real part?
Add or plus and then selectors.
What are Z1 and Z2?
Z1 and Z2 are complex numbers.
Do we need the value of rectangular? Need to make complex numbers, or do we already have them?
Well, remember, right here we're just defining a procedure, right? We would, if we were going to use it and apply it, we'd need to make a couple of complex numbers to try it out on.
But within the body, if we've already been doing two complex, oh, we're making the result.
We're passing them in. We're passing back the results. So we're getting two complex numbers and returning the result of adding those as one complex number. Question?
Do you know that they are in rectangular form?
Exactly. Let's assume that they're in rectangular form if we're going to be calling add complex, right? Because what's going to happen if we don't know what format they're in? Well, then we don't know what we're using, and this is going to work when we've got one in polar form. These are going to work in rectangular. So let's assume for now that it's in rectangular form. And as we progress through the lecture, you'll see how we can actually make it so we don't even notice which type we pass in. We'll create some converters and some tag data and all sorts of fun stuff like that. Yay. The cheer goes up from the crowd. OK. We're going to add two things for the real part. the real of Z1 and the real of Z2. Real part Z1, real part Z2. Okay. So that's our real part to pass in to make from real imag. And now we need to figure out what the imaginary part is. Same thing, except we're adding the imaginary parts. And I hear, that's the abstraction. And indeed, it is the abstraction that we're using. Oh, love the abstraction. Okay, let me get the comment right. We love the abstraction. Abstraction is good. Okay, so that's how we would add two complex numbers if they were in rectangular form. Now, how would we multiply two complex numbers? And let's assume that they're in polar form. So they're going to be in this land, which means we've got these selectors and that constructor. So what are we going to do?
Make
From magnitude and angle. Okay, so the first thing we need to pass to our constructor is the magnitude, which will be the magnitude of the first times the magnitude of the second. And now we need to figure out the angle. Well, we're representing in polar, we're only representing R would be the magnitude, and then we're representing A. The E to the I we're dropping out of our notation because it's going to be the same every time. We don't need to keep that there. So all we need for the angle, well, let me circle it in the right place, is that term up there. The angle of the first plus the angle of the second. Will you believe me if I tell you that subcomplex and div complex are very, very similar? Okay. They're also on the handout for today. They're in the book, and you guys could also write your own copies of them, I'm sure. Okay. So, add and multiply. But we've got some issues here. And those issues are, if I want to multiply, I have to have them in polar form. If I want to add, I need to have them in rectangular form. But that's not a great system, is it? Yes.
And why can't you just always use rectangular form? It's not that hard to multiply and divide using rectangular form. And then you don't even have to calculate angles or magnitudes.
Okay, so why don't we just do everything rectangular? And the answer is, well, make a really bad lecture example.
Or why don't we, in our abstraction layer, have the thing that pulls out magnitude and angle, pull it out from either or, it can recognize which one it is.
Exactly. Why don't we change our system so that real part, imag part, magnitude, and angle somehow will pick out the right thing. So if we happen to pass in rectangular coordinates here, we'll somehow get polar coordinates out. Okay. Now, if I'm going to pass in rectangular coordinates here or polar coordinates, how do I know if it's in polar form or rectangular form? Tag it. Good. Okay, we need to put something there to tell us. Well, you know, given that the lecture's called Tagged Operators, that's a really great thing. So let's tag things. Where tag is just going to be, we actually saw some tagging already. Where did we see some tagging occur? With frames, right? Because we had the first thing, we made a list where frame was the first, and then we had other stuff. So we've already seen some tagging. Okay. Okay, so we have some conversions. x is r cosine A, y is r sine A, r is equal to square root of x squared plus y squared, and the angle is the arctan of yx. Okay, just we have these. Now, type tags. We're going to define a procedure called attach tag. It's going to take two things. It's going to take in a type tag, and it's going to take in contents, what we're going to attach the tag to. Yeah. So, we've got a tag and we want to attach to some contents. How can we do that? Cons. And the cons the type tag to the contents. Does it have to be cons? Does it have to be cons? Do we need to use cons?
It could be the first element of the list.
Right, we could make a list where the first element of the list is a tag, which I believe is what we were doing with the frames. Okay, it doesn't matter so much if we use cons or a list or some other thing, as long as we have matching. Does it? Selectors, right? Our constructor, we can do whatever we want in the constructor as long as our selectors pull out the right pieces. Now, cons is going to be the simplest one for us to implement, so we'll do that. But it could be something more complicated if we wanted it to be. Or it could even be, like we saw a few lectures back, how we could write cons, car, and coulda in terms of procedures. Okay. So we could do something like that if we wanted to do some sort of higher order procedure thing. But cons is very simple, very neat. Let's go for it. So if we've got attach tag written like that, what is my procedure type tag on some datum going to do? How do I pull out the type tag? The car. Okay. What I'm going to do is I'm just going to provide a little bit of error checking here. And I'm going to make sure that I have a pair. Because maybe the user's messed up, hasn't realized they need to put it into a tagged form. If I don't have a tagged form, then my operators aren't going to work on it properly. So I'm going to check to see if I have a pair. And if I do have a pair, then I'm going to return its car. Otherwise, I'm going to return an error that there's a bad tag datum in the procedure type tag, and then print out the datum. Okay. Similarly, we could write contents. So what's contents going to do? Return the coulda. So we'll do the same sort of error checking. If we've got a pair, return its coulda. Otherwise, we'll return an error. Question for you. Is this going to check all possible errors? No. Because we could pass in a pair that still doesn't have a good tag at the beginning, right? So it'll check some of our problems, but it actually won't catch all of our problems. Okay. So now that we've got a way to attach a tag, how are we going to use them? Well, let's write a couple of procedures, rectangular question mark and polar question mark. And what these are going to do is tell us if we have a rectangular number or if we have a polar number. Okay, this is going to ask, is a complex number in rectangular form? So what would this procedure look like? Well, have I talked anything about what our tags are going to look like? What we're going to do is we're going to put rectangular as a tag if it's in rectangular form, and we're going to put polar on if it's in polar form. So these will be our tags. So given that now we know what the tags are going to be, what are we going to check? I hear, will it be equal? Will it be EQ? Will it be EQV? We can actually use EQ on symbols. Okay, so EQ, what two things we're checking to see if they're EQ? Type tag. The type tag of Z and the symbol rectangular. Similarly, we could define polar question mark as okay, I hear from the front. How about not rectangular? Right, what if we had a third type of representation? Then we'd have to go back in and change polar. So it's better to make it specific to the particular package that we're now working on. You can think of us as having a package for rectangular numbers and a package for polar numbers, and maybe we'd install a third package for yet another representation of complex numbers, if there is such another representation of complex numbers. I'm sure we could come up with one.
Bob must have them.
Okay, so moving on. Okay, let's assume that we do now have these. Well, we still have problems. If we look one level down on the board here where I erased before, we had some constructors and selectors, real part, imag part, magnitude, and angle. We need to change those. So what we need to do is we need to actually write one to pull the real part from a polar number and the real part from a rectangular number. And the way that we'll pull a real part, an x, from a polar is by providing this conversion. The way that we'll pull an imaginary part from a polar is this conversion. The way that we'll pull the magnitude out of a rectangular is by doing this one, and this will be pulling an angle out of a rectangular. So we can do some conversions. So we can write selectors. But first, let me write the constructors. This is a lot easier to write the selectors once we've seen the list structure or con structure that we're using for the constructors. So let me define something called make from real, imag, rectangular. Okay. So this is telling me I've got a real part, an imaginary part, and I want to make a rectangular number, rectangular representation. So what am I going to do with my x and my y? What could I do with my x and my y? I could do many things, but let's go for sort of the simplest. If I have a real and an imaginary, the real is x, imaginary is y, and I'm putting it in rectangular form, which is the x and the y. So I've already got x and y. What do I want to do with x and y? Store them, cons them. We just cons them together. We can make a list of them. Okay. Similarly, we could define make from mag angle polar. Just going to take an R and an A. Okay, so if we're making a magnitude and angle into a polar, that's our simpler case, right? Because we've already got the magnitude and the angle, so we can cons them together.
Might you want to normalize so that if you have 0 R there, you don't
normalized to 0 angle, like we did with GCD of primes?
Otherwise,
Zero
you might be
bar.
saying 0 and 5 degrees is the same as 0 and 10 degrees. But that's, I don't know complex numbers. Are they really different? Otherwise, when I multiply,
Zero, yeah.
0R would not be complex, it would just be
0.
There'd be 0 imaginary.
Right, there's nothing imaginary if it's 0.
but how do we force that? If I sent in 0 and 5 degrees,
There won't be any simplification in our current system. We'll have unsimplified numbers, you know? Yes, we don't simplify things here, that's right. We just make them more complex. Okay, so make from real imag polar. Okay, so now we start to get into needing to do some stuff. But let's go back for a moment here. Did I forget something? Ah, we didn't tag the data. We did not tag the data. Let's tag the data. How do we tag the data? Because then I'm going to error out on these lovely little selectors over here. Going to attach tag rectangular. Now to the cons xy. Better. Let's do this one too. And remember, we need to tell the system if we've got what type of representation we've got. Just by looking at the two numbers, it's impossible to tell which form we're in. It's going to be two numbers. It could be in either form. So I'm going to add tag polar to the cons xy. Okay, so here we're making a polar number, so the tag we'll attach is polar. Okay, now we're going to cons two things together, but we've got x and y, and we need r and a. So r is going to be the square root of x squared plus y squared. So we're going to cons the square root of adding the square of x to the square of y. 1, 2, oops. Okay, and what's a? Arctan?
Was that 1 times?
I think y comma x.
Y comma x, yeah. So you can call a tan y x.
Why would arctangent take 2 parameters?
Yeah.
All right, do you guys remember there was a footnote on problem set 2? Oh, yeah, that footnote, way back when, like a week ago? And if I recall the footnote correctly, arctan, yeah, so you can say arctan of x is the same, rather atan, I should write, since that's what scheme say. So atan of x is the same as saying atan x1. And so we've got our angle, and then we're passing in the magnitude. So we can vary.
Isn't x and y, aren't they just x and y coordinates and angle whose tan is the opposite of adjacent? Like that?
Oh, yeah, I'm sorry, goofing. Do, 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 do.
And so y is opposite, x is adjacent. And so we convert it to rectangular to polar.
So this is our side. This is our r, because we've got x squared, y squared, square root. And then if I drew the triangle a little more intelligently.
Yeah, and is your opposite, actually, it's right.
Okay, it's right. Great. Moving on.
It's still got the same
Great, we're right.
angle whose tangent is the magnitude of the y over the magnitude of x.
Right.
So
Okay.
But that's not what we define arctangent as. I mean, arctangent
Yeah,
is the inverse
it's the
tangent,
angle.
where you give it.
arctangent is the angle whose value is the opposite of y over
Whose
x.
tangent
Is
is
y over
right.
x.
Right.
So
Okay, so
the
is that what
arctan x
Steve
over
is
1
doing
makes
to
perfect
arguments?
sense.
Is it dividing y by x?
So
So when you take 2
So
for x, I
arctan-
guess it's just a
Today I don't bring R4 with me and I lose.
So arctan x and arctan x over 1 are fine because it assumes it's the same thing.
Right. Circle.
Exactly.
So the
Maybe
length
one.
would be 1, so
Yeah,
But instead it could be.
the radius 1.
yeah, exactly.
Don't you give it the angle?
So we're trying to get the
We're giving it x and y, which are the lengths on the x and the y axis. The x. If I actually drew, yeah. Well, anyways. When a square isn't a square. Okay, a tan. Check. Check. Okay. Yeah, it's weird. Moving on. All right. So that's how we make real imaginary polar xy. Do you guys believe me that making a magnitude and angle into a rectangular would be somewhat similar? Or shall we write it? The code you've got. You've got the code. All right. Given that. Let's define the selectors. Real part, rectangular. So this is, if I'm given a number in rectangular format, how do I get out the x? Well,
We don't want just generic real part and then check our tag.
okay, do we want generic real part and then we'll check the tags? Well, if we use generic real part, what's generic real part going to use? Somewhere we need to get to our base case, right? Because if this calls generic real part and then generic real part somehow needs to call something specifically for rectangular, we're going to be sort of spiraling. We had written a generic real part, but basically we're going to have to.
The word rectangular.
We've used generic real part, but we haven't written it yet.
Yeah, I see that.
Okay. So let's assume if we're calling something real part rectangular, if we're going to be calling this routine, the system is stripped off the tag. The system already knows that we're using a rectangular number because it has actually called this procedure. Right? Because we're not going to call this unless we know we have a rectangular number. So when we come in here, this complex number is just going to be the contents. The tag is already stripped off. Okay, so let's assume the tag has been stripped off if we're calling this selector. So given that, what are we going to do to pull out the x part, the real part? All right, the car of the contents. Here, car. Do we want the car? No, just want the car. Okay. We wanted the imaginary part of rectangular z. Gooder. Okay. Now, here comes some fun stuff. What if we want the real part of a polar? So we know we've got a polar. That's why we're calling this procedure. We're going to need to do a conversion. So that's this. Okay? So the real part of a polar. Of course, I didn't write that one down, but hey, we can do it. Okay, so the real part of a polar is going to be the result of multiplying So it's going to be the magnitude polar z multiplied by the cosine of the angle. Okay, so that's how we're going to get the real part from a polar number. What if we want to get the imaginary part of a polar number? Here, change cosine to be sine. So I'm going to multiply the magnitude polar z times the sine of the angle polar z. And in this way, we could build up how many selectors? How many do we need? Right now I've written 3. How many more would we need?
1 more. 3 more.
I hear 1, 3, and 5. Do I hear 7? 9? Okay, we need to have an imaginary part for rectangular, and then we need to have the 4 to pull out the magnitude of a polar, the magnitude of a rectangular, the angle of a polar, and the angle of a rectangular. So we'll need 8 altogether. Do we want to write them all? No. We could write them all. Do you guys want to see any of them in particular? Pick your favorite one.
The reason why you're trying to pull out the real part of a polar is in case you wanted to add 2 polars.
Exactly.
Okay.
Right, so that we're going to, at some point, we're going to try to have them be in the same format at least, right? So, you know, we could try to add 2 numbers in polar form, but we need to convert them both because our add routine uses them in rectangular form. Or we may be trying to add 1 rectangular and 1 polar, in which case we would only need to convert the polar one. Okay, so the conversion is going to be done by our selectors. So that add complex, mul complex, subcomplex, and div complex will be exactly as we wrote them at the beginning of class. We're not going to need to make any changes to those because those just called out real part and imag part, or magnitude and angle. And by the time we get to the end of this class, we'll be able to just say real part, magnitude, angle, and it's all going to work out fine and call this stuff. Everything will be happy and beautiful. Do you believe me? No. Great. Yes?
Is the tagging all internal, or are we going to, I don't know where the tag is.
Where is the
Is it all
tag?
internal to these procedures, or is it something we print out with data, or is it?
Well, so we're never going to, once we get the result, let's say we build up some number somehow. When we return the number, will the tag be on that number we return or not?
I don't know.
Anybody have a feeling for that? I hear no. I'd rather hear something else. Okay. Why? Let's think about it. So if we're passing in, let's say we're calling add complex, and we've got some tag for rectangular number, and then we've got some tagged polar number. What if add complex returns something without a tag? Could I then use it in any further computations? No, because so if we return this without tags, then all of a sudden we're back to this case where we've got a number and we don't know if it's in rectangular form or polar form. But if we return it tagged, then we know what type of format it's in.
So you say we, you mean the system or us?
Yeah, you know, sometimes we identify it a little too closely with the scheme interpreter, I suppose. So the royal we, the scheme interpreter, and I, will return to you. Don't you know I'm sitting in the back room when you guys are typing evaluations in, actually spitting them back out at you? That's why you don't see me sometimes. I'm in the back room working so hard, you know, spitting these things out. Yes, yes, I am cruel. Well, that's a Dimitri effect, actually. Now you know. Because I know, oh, Dimitri's there, everything's right now. Explains why, yes. Okay, so scheme needs to know what type of numbers we're operating on. So when we write a procedure to add two complex numbers, we'd like it to be returned as a complex number in whichever format it's being. We want to know what format it's being returned in. If we're adding, we're going to return a number in rectangular form. If we're multiplying, we're returning something in polar form. But we need to have that tag there, because what we'd like is our system to have the property of closure. So once we operate on numbers, we'd like to be able to operate on those again. And if somehow we forget to put the tags on, if we haven't written a procedure that has the tags put onto the data, then we can't use those numbers again, because we would no longer look at it, just know by looking at a const cell 3, 4. If you look at that, you don't know, is that rectangular form, is that polar form? So that's why we're going to have another const cell that has either a tag polar or is going to have the tag rectangular. So if you run this system, if you take the code and you run it, you'll see the result of adding two complex numbers is going to end up printing as this constructor. And you'll see either polar or rectangular at the front of the lists that are the list of return the constructor that's returned.
Okay, so 3, 4 is the contents now?
Yep.
Well, is the text. Okay.
So if we wanted to make a complex number, so we could define, let's see, well, maybe I could call this rectangular 2, 3. Well, I could define this as, we have some constructors somewhere, don't we? Here we go. We've got a real and an imaginary. We want to make a rectangular number. So I'm going to call make from real imag rectangular on what? I'm going to make a number with 2, 3. 2 and 3. So let's say I've made that call. Okay. If I've made that call, what does my box and pointer diagram look like? Well, the call to make from real imag rectangular takes in two numbers. In this case, we pass in 2 and 3. We attach the tag rectangular onto the cons of x and y. Well, attach tag, the code's on your handout, but if you recall, attach tag was just a consing of the tag to the contents. So the contents is going to be the const cell 2, 3, and then we're going to cons the contents with the tag rectangular. Okay, we don't really need to have the quote there because it's just a symbol rectangular. Okay. So that is going to be what R23 will be bound to. And if we define that number and then we print it out, we'll see that's printed out as some sort of list cons with dots. And in fact, it'll actually print out like this. Okay, so that's how it'll print out. Remember, this would be dot, paren like that. And when scheme is printing, it axes out the dot paren and then the match. Yes?
Maybe I'm missing something really simple, but why are the 2 and 3 in the same set of boxes instead of 2 related boxes?
Because in our constructor over here, we said cons xy. They'd be in different boxes if we had said something like list xy. It's just the way that we chose to build it up. And choose anyone. If you do a cons cell, it requires one less check down the cons structure, right? Because if we did it as a list, then to pull out y, we'd need to do a catter instead of just a simple cdr. It's not going to make that much of a difference. For me, either one is the same. I mean, they're just box and pointer diagrams, right? It's just a matter of how we're pulling the stuff out from it. So if you have a list, then you need to pull out the car and the catter. If you have a console, you need to pull out the car and the coder. So as long as they match, it doesn't matter. Yes?
Are we assuming that the user is inputting these things in a regular manner so that the real part is always sort of first and the imaginary part's always second?
Right. The user is going to have to, in order to make numbers to operate on, the user is going to have to use our constructors. The user is going to have to define. The user can't just call add complex and then pass in 2 numbers. The user actually has to build complex numbers up for us to use in our procedures.
But they couldn't put, like, 2i plus 3. They'd have to do 3 plus 2i, or could they do either one?
They have to give us the real part first and the imaginary first, because that's what the constructor is expecting and that's what it has to be. Okay? So if they change that, then they're just passing in the wrong thing. They're going to get answers that aren't what they expect. Of course, whether or not they'll expect the right answers when you're operating in complex numbers and everything starts going, through 3 iterations, who knows? But it's not going to be what you expect. It has to be X, then Y. Just like in 21, when we had our list representation, we had to have, if your constructor said that the first card was first and then the total hand was the second element of the list, it had to be that way. And if you built it up where you had the total first and the first card after that, then everything would start blowing up because you'd be pulling the wrong pieces of information out. Okay. Similarly, we could define polar 2, 3. Or we could change the numbers, I suppose. Polar 4, 5 to be make from mag angle polar 4, 5. And that's going to give us this box and pointer diagram. Okay. So the only thing that's differentiating, if we didn't have tags, the tags weren't returned and they weren't passed in, then we'd just see a console 2, 3, or 4, 5, and we'd have no idea what we were representing there. Check? Okay. Good. Tags are good things because they're going to allow our system to differentiate the types of numbers. Yes?
So for me to see what 5 is as an angle.
Radians.
A number of radians.
5 radians?
Yeah.
Yeah, so it's just less than 2 pi.
Yeah, so almost 360
Okay.
degrees.
Okay. Good? Happy? Any more questions? Should we do some more? Okay. Given all of this, that we actually had completed all 8 of our selectors and all 4 of our constructors, let's write real part and imag part, the general ones, to use all of these pieces that we've now built up. Okay. Now, if you think back a few minutes, I had said that we're going to know if this is called that we have a rectangular number. Right? The system will have passed us here. So here we are in real part. This is the place in which we decide whether we're going to call real part rectangular or real part polar. How do we do that? Let's check, right? Do you remember what we have to test a number? Rectangular question mark. So we can say rectangular question mark z. Okay. Now, if the number is rectangular, what do we want to call? What do we want to do here? Ah, yes. Real part rectangular on the contents of Z. Here's where we strip off the tag. Oops, sorry, shouldn't have ended that. A little over rambunctious there.
So now the reason why we would want to do on contents rather than on the cutter is to maintain that abstraction barrier?
Well, because once we call real part rectangular, now we know what the real part is, right? Whether it's the car or the cutter.
Would be the same thing.
Sure, but we've just blown up the abstraction barrier, right? So if we just say rectangular is the cutter of the contents of Z, then we've lost that abstraction barrier. Because in fact, it may not be the cutter, right? It could be the catter if we had represented it as a list. Or we could go and change it and represent it as some high order procedures. Okay, so we don't want to go through that abstraction barrier because that could change later on us, and we don't want our code, which is just on top of it, to be affected by any changes. Because basically all the constructed selectors are is some sort of contract that says, if you call me and you pass me a complex number that you've made using the constructor, I will give you back a particular part of it. And it says nothing about the underlying representation. All it just says is if you give me a number that's been built up using the constructor, I'll give you back the right part. And then all the underlying representation stuff can change. Okay. Okay, now after we check a rectangular, we should check for polar. And if we have a polar, we'll get its real part. Real part polar on the contents of Z. Okay, what if I had a third representation? Or a fourth, or a fifth, or an eighth? Well, that's where it would start going in here. I'm going to have an error clause. How this handles what?
Well, we haven't defined rectangular.
Yeah, we did. We defined rectangular probably about a half hour ago. It's also on your code handout.
When you call real part, is Z tagged?
No. The reason well, Z is tagged, rather. But when we call rectangular, the reason it's not tagged is we're calling contents. And contents, if you recall, when we had written attach tag at the beginning, it cons a tag onto the contents. And then when we had type tag, that was a selector that pulled out the car of our tag structure. And contents pulled out the cutter of our tag structure.
His head was in the way.
I see, yes. Blame it on your fellow students. Way to go. Otherwise, we have a bad type in real type, and then we can pass back Z. Perhaps you should consider shifting your seats a bit. Okay, so that's what's going to pull out the real part. So now, because we've defined real part, our add complex, small complex, div complex, and subcomplex all can stay the same. Because those just pulled out a real or imaginary part. Because we built this underlying representation, now it doesn't matter if we're trying to add a complex with a polar, because this underlying representation will take care of stripping off the tags and returning the right number, and it will do the conversions if we need it to be done. Isn't that beautiful? Okay. So we could similarly write imag part of Z, which would be cond. Again, check to see if we've got a rectangular. If we do, it's not an image part, it is an imag part. On the contents of Z. Then we check, do we have a polar? And if we do, then we call imag part polar on the contents. We start building systems like this. This is a good time when you start having some sort of consistent naming of your procedures. Because it makes it easier for us to write it. I don't have to go back and look and say, what the heck did I call this procedure? Because I know that I'm calling it what I want and then the representation. It's making it easier for me to write the code. It'll make it easier for the code to be read, too. And then else will error.
Well, what do you call those procedures? For example, they're not like selectors, right? They're just...
Well, this is a selector. That's the selector to pull the imaginary part out of a tagged number. This is also a selector. That's a selector to pull the imaginary part out of something that we already know is in rectangular form. So just the con cell with the numbers inside of it representing a number in rectangular form. So these are both selectors. And we're not using any constructors here. So we have one selector calling another selector. Okay, if I were to write magnitude and angle, similar?
Yes.
Believe me? Yes. Want to write them anyway? No. Okay. Okay, there's one final thing that we need to do. The final thing that we need to do is we need to decide if, given a choice, do we want the number to be in rectangular or polar form? So we could actually force, let's say the user is trying to define a number and is telling us that they want that the number's in rectangular form, that they're giving us x and y. Well, we could immediately force it to be in polar form. Right? Similarly, if they gave us polar, we could immediately force it to be over. But sort of the path of least resistance is whatever we're given, let's keep it in that format. Let's not convert it until we have to. Okay? So we're going to define make from real imag. Remember, this is a constructor that was called by add complex, subcomplex, div complex, and, well, no, rather, make from real imag is only from add and sub. Okay, so if we're calling make from real imag, let's just keep it as a rectangular number. So how would we build a rectangular number in our nice tag system from x and y? Very good. We're going to call make from real imag rectangular xy.
Just sort of adding another word at the end of the function name and making it more complex than we need to. Yeah, I'm not sure how that clarifies anything.
Well, let me draw the abstraction barriers.
Yeah.
Oh, if you think this is fun, wait till we get to metacircularity. When you write a scheme interpreter in scheme. That'll be fun. Let me get my abstraction barrier picture. Okay, so here's our abstraction layers. And remember, at the bottom of it all is just me sitting in the back room. So here we have programs that use complex numbers. And their view of the world is that they're going to use add complex, subcomplex, mul complex, and div complex. They do have constructors because they can see make from real imag, and they see make from real, make from mag angle. So in fact, if you're here at this level and you wanted to define a rectangular number, you would say, I want rectangular 2, 3. I'm going to define that to be make from real imag 2, 3. Okay? And if we called make from real imag rectangular here, we're violating the abstraction barrier. Okay? Because we don't have that here. Up here, we can use these, and then the constructors and selectors that we have are make from real imag, and then make from mag angle. And then we have real part, imag part, magnitude, and angle. Okay? And that's what we get to use if we're up here using complex numbers. Yes?
And if you're up there in that program, how does it tell the add complex how it's putting the data in, if it's putting it in rectangular or polar?
Because add complex, basically add complex, let me just rewrite that procedure up on the board. So we're adding two complex numbers, Z1 and Z2. We define this to be make from real imag plus real part Z1, real part Z2. And then the second part is going to be adding in the imaginary part of Z1, and then the imaginary part of Z2. Okay. So, this was add complex. But if you recall, well, make from real imag is going to call make from real imag rectangular and put the tag on.
Z1 and Z2 are already in rectangular form?
No.
It doesn't? It's gonna
No, because remember we had written real part and imag part, which I've erased to put the abstraction barriers there. And what that does, real part says rectangular question mark. And if it's in rectangular, then it will strip out the right part. And then it will check polar question mark. Okay, so that's, so at the top level, we don't care about the tags. We're not seeing the tags. Well, in fact, you are seeing the tags, right? Because we return an answer that you'll see the tag on. But we don't have to deal with putting the tags on ourselves. We don't have to deal with taking the tags off. Because remember, we talked about the result of this will actually print out rectangular, and let's say the answer is 2, 1. It'll print something like that. So the user will actually see this tag, but they'll look at it and say, okay, this is in rectangular format 2, 1, and they don't care if this is a tag and this is being stripped off later or anything like that when we're up here at the top level.
But that program that calls add complex and puts in Z1 and Z2, doesn't it have to know whether it's putting in the numbers in real, in rectangular?
Add complex doesn't care if they're rectangular or polar, because these calls are here to real part and imag part. And that's where we handle what type it's in. Because add complex wants to add two real parts together. But remember, we have real part polar that can convert a magnitude and an angle over to give us an x. And we have imag part polar that can convert the magnitude and angle into the y for us.
The Z1, Z2 is not X, Y, or RA?
No, Z1 and Z2, these are tagged complex numbers. Right, well, because remember, so over here, if we wanted to make a number to call, we would define R2-3 as a make from real imag 2, 3, and then we could do add complex on R2, 3. We could add it to itself.
So that's above the abstraction barrier.
Right. So the user, if they're dealing with complex numbers, they are going to have to construct them. Okay. They can't just pass in 2 and 3. So they'll build it here, or they actually, they wouldn't need to define it. You could actually also call add complex on if you wouldn't mind, MFRI 4.5 and MFRI 2.1. Okay? Right, but somehow, right, the user needs to still call a constructor. So it's not like the user could just magically pop in 2s and 3s. Right, yeah, so somewhere the user has to say whether it's in rectangular or polar. Yes?
If you're writing like two vector form real numbers with the magnitude and the angle.
Yep.
Shouldn't you return? I mean, wouldn't the user be expecting to be returned a real number that mirrored that number?
They could be, and certainly we could change all of our routines that if we're past 2 complexes, we want to return a complex. If we are past 2 rectangulars, we'll return a rectangular. And if we're past 1 of each, then we'll pass whichever one is easier for us. And we could certainly rewrite all the code to do that. Okay? And the way that we would do that is, well, here we'd have to add an extra sort of layer on top of it. Right? So we'd have to add something that if they were both typed as complex, would need to say, basically check the tags here. So we'd add basically another abstraction level inside of it. Would build yet another level on top of it. But sort of between here and the lower system, we'd have to build something that would check the tags and decide how we wanted to return the number.
I mean, this seems like it's kind of porous because we're getting this back out. Shouldn't we actually have something like a print complex that would give us in like e to the I notation or x plus iy notation rather than this internal list representation?
Sure. We could basically make instead of make from real image, we could have print real image. Okay. So if we wanted to define that. Okay, so if we want to print a real image xy, we could spit I display y. Okay. Right. So then instead of spitting out this as our answer, we would print it. Now, if we just printed the number and we didn't spit it out, then we'd start running into trouble if we were trying to perhaps multiply complex, and we're going to multiply the result of adding 2 complex numbers.
My question hinges, I understand that.
Okay.
My question hinges on preserving the abstraction barrier so that the user of the program doesn't see the internal representation. And we should have some way of hiding that.
Sure. Well, what we could do is that we could call a printing routine first, and then we could return the actual object made up. But remember, the user, because of the way schema is, will still see value rectangular 2.1.
This print routine that would be at a lower level of representation, right? That wouldn't be the upper abstraction level. You should take that complex number.
Right, because we need to know whether or not we were going to deal with complexes. Or I was just saying, in this case, if we knew we had x and y, this would be a simple way to write it. But yes, we'd need to build, just like we built up the layers below for our constructors and selectors, we'd need to build layers for the printing routine. So what we would have is, remember we had real part, image part. So print real image would have to check to see if the numbers were tagged. And then it would have to strip this up. So in fact, in that case, if we did print real image in that sense, then we'd be passing it a z, and we'd be pulling out the parts of it here after we decided what type it was.
Can we continue the abstraction layers now?
Sure. John would like us to get back to business. Okay, so here are our programs that use complex numbers, and this is the stuff that they get to see. Now we have our complex arithmetic package. Okay. And it has real part, image part, magnitude, and angle. So I wrote these up here. These actually, if we were really drawing this properly, would really belong more here. Because, well, no, the constructor should be there, but the selectors the user's not going to use. The users need the constructors, but they don't need the selectors.
So, for real part, match part, magnitude, angle, the user doesn't input those.
Right, so basically what you can think of as this stuff here is these see this, and that's what passes it to this. Now this is obviously going to see the stuff in this layer. It can see the stuff up, and it can see the stuff down. So it's seeing the stuff up. Now these real part, magnitude, blah, 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 is what allows us to go into either rectangular land or into polar land. Okay. So when we're up here, we can access stuff that's here through this here. But there's some stuff that's hidden from us. And then when we're here, by using these things, it's what allows us to get here or here.
So did I understand correctly? You said the make from real image, the mag angle, real part, image part, magnitude and angle really should be in the...
Yeah, so basically...
Would they be in both? Or I'm not really clear on where exactly. Because the user can use them.
The user can actually use anything, right? Yeah, it might be nice to actually... What would make this really a lot neater is if we created something called maybe make complex. And we could define something called make complex, and we could just say you always have to give us, you know, an angle and a magnitude, or you always have to give us a real and an imaginary. Or we could define something called make complex. Basically build another layer on top of it to sort of hide that lower level.
This is where it'd be nice if you could do some pattern matching on make complex. Like
Right.
if they didn't happen to both just consist of two numbers.
Right.
Right. If they could.
Right, if they actually, so actually, yeah, it would be a really nice thing, just like we'd have a print complex. We could have a make complex where, you know, they could give us something like 2 plus, you know, I3 or 2 plus 3I. We could pull out the relative parts of it, and that would make this nicer, certainly. Because then that would really not violate the abstraction barriers, because we'd say make complex, and then would pass 2 plus I3, or we would pass in, you know, 4E, you know, whatever, I2. Something like that. Okay, and that's when pattern matching would be nice, you're right. And that would basically really clear up our layers for us, because then the user wouldn't be calling this at all. The user would just say, make complex on, I could say 3 plus, you know, I2 or something like that. Okay. And that would be much, much neater. That'd be a much better abstraction, sure.
We could do that with the dot notation. Say the 3 arguments, the final one is a quote I, and then it's the list. We're just in one.
We're passing in a list of 4 things here. I actually spaced them out to make it a list of 4 things.
2 or 3 arguments using that kind of a dot notation, which is open-ended.
Well, this is only one argument. This is a list. Or the other one, I think I wrote 4.
There's a mechanism right now that we could use to say.
Yeah, there is a dotting notation. So if you say lambda x dot args, okay, what this says is I am a lambda and I am expecting at least 1 parameter. And then you can pass me 0 to as many as you want, remaining arguments. And what the dot notation does is it will bind the first parameter to x, and then it will bind args to the list of the remaining parameters, the remaining arguments. Okay, so if we wrote a lambda like that, then we need to go down and cut her down the list or know how to break out the remaining arguments there. But yeah, we have the dot notation. But make complex would not need to make use of that dot notation because we're only passing it 1 argument, but the argument is a list. And then we could pattern match that list. Other questions? You guys all look at me like, yes, it's Friday.
You're still working on this abstraction thing.
The abstraction thing is done.
Is that it?
Yeah, that's it. And then down here is where we have things like real part rectangular, image part rectangular, magnitude rectangular, angle rectangular, and then here we would have real part polar, image part polar, magnitude polar, angle polar, et cetera, et cetera. So it'd break out into these two halves.
But where would we put our tag functions in this scheme? Do you have a sense of where those fit, conceptually in the layer?
Where do the tagging functions go in this drawing?
They're sort of parallel to it. Because the tag is...
It'd be down in the rectangular and polar one.
Well, the attached tag, contents tag, tag data.
I mean, it's not below rectangular and polar to the extent of moving, because tagging is generic.
It's used by
Sure.
Right, but it can be used by the package.
Well, but it's not used by the complex arithmetic. I mean, this, yeah, actually it is used by that, yeah. Yeah, put it to the side. Okay, so here, side, tags land. It's cold.
That thing would like circle around itself. Oh God, that'd be weird. Where are you going? I'm going 2 Pie Street. So back to this thing at the top of this board. So you consider that basically a placeholder for the potential of future changes to the interior structure of rectangular. Because that doesn't do anything other than make an alias to a function name. But you want to keep it there as a...
Well, what I'm keeping it there as is it's breaking out for my user. Right? They're not seeing that they have to call something in rectangular, because we could just as easily make it into polar form. This is sort of our path of least resistance, because we have an x and a y, and we're just making that into a rectangular number. We could have just as easily said, make from real image polar. Doesn't make a bit of difference.
But not x and y, then.
Of course you could, because we have that routine, make from real image polar. And what it does is it converts x and y into the magnitude and the angle. Okay, so this here is just some internal representation, and we've just chosen that if we've been given an x and a y, then we choose to keep it in rectangular form. But we could easily just force everything to convert over to the polar, or everything to convert over to rectangular. Yes?
Would be a better name for that one, make real image, and then there would be another one, make xy, because at that point you know what you are entering. It actually should go to rectangular or polar representation.
What we know at this point is that we have x and y, but we don't know what representation we're going to, unless that's how we define it. The person calling this, if I'm calling make from real image, I know that I have an x and a y representing a real and an imaginary part of a number, but I know nothing about how it's going to be stored internally when I call that.
So what you're asking is to make it represented as real and image.
No, I'm asking them to make, maybe a better name would actually be make complex from real image. Because I'm just saying, I have a real and imaginary number, so make me a complex number. That might be a better, but it'd be longer and would write even more on the board.
Now, if you decided to made a command decision to say that, okay, we're storing everything in rectangular, you would be able to dispense with the tagging and just have your polar selectors and constructors do the math inside of them.
Right, yeah, right. We just change the constructors and the selectors. The tagging is a nice idea, because then if we wanted to add in a third representation, we could. We don't have to worry about it. But sure, if we want to represent everything in one way or the other, then you don't actually need to have the tagging. And in fact, if you look in the book, and I think it's section 2.4, they actually start out the discussion of this by saying, you know, Alyssa went off and wrote the package this way, Ben went off and wrote it that way. Now let's bring their worlds together. Yeah, so today we talked about bringing it all together. But we didn't talk about the separate packages, so they would actually be there and you wouldn't need to do that stuff. Other questions? Okay, that's all.